morning friends. We are back with fluorescence spectroscopy again. So, in our last class we talked about this excited state acidity. Now, all of us know about the acidity. What we generally talk about is the acidity in the ground state. Okay. Now, excited state acidity means it is different from ground state acidity that we already have talked about, and moreover in the electronically excited state, since the electron distribution in the molecule is different from that in the ground state, so it ought to affect the acidity of the system. Acidity of the system means how easily the proton can leave the system. That means if you think of a molecule, so how easily it can donate the molecule, and since the excited state properties are different, so acidity will also change accordingly. Now, in this regard we talked about acidity of phenols, that phenol in the electronically excited state is more acidic than in the ground state, and this is because of the fact that the conjugate base is more stable in the excited state than in the ground state. Because when we talk about acidity, now we always talk in terms of like say RH. When it gives rise to proton, then it is R minus plus H plus. So, if R minus is more stable than this one, than whatever is in the left hand side, then this equilibrium will be shifted towards the right hand side, and as a result the system will show acidity. Now, apart from this excited state acidity, in the electronically excited state, various processes may take place, various interesting phenomena can be observed. Okay. So, of which one is the excited state proton transfer, which is in line with the excited state acidity. Now, excited state proton transfer means it is basically transfer of proton from one part of the molecule to another part of the molecule. Okay. So, suppose you have got a molecule say like this. Okay. So, I am not going to write the details of it. Suppose here we have got say one OH, and suppose there is another acceptor of hydrogen at the other end of the molecule, say acceptor. Then what will happen that this hydrogen may be, this proton, basically this proton may be transferred from here to here, so giving rise to another form. Okay. So, this transfer of proton that may occur in the ground state, and that may also occur in the excited state. So, we will talk about this excited state proton transfer, and generally we will focus onto the excited state intramolecular proton transfer. Okay. Intermolecular proton transfer may also take place, but intramolecular proton transfer is can be more interesting. Now, proton transfer is one of the most important elementary reactions in chemistry and biology. The role of proton in the course of proton transfer, whether it is active or passive, has been the subject of intense investigations. Proton transfer is a process in which a proton gets transferred from one atom to another in the ground state or in the excited state. And the excited state intramolecular proton transfer, which is basically in the short form is ESIPT, occurs in the electronic excited state of a molecule where a transient heterocyclic ring is formed by intramolecular hydrogen bond between a hydroxyl group, that is a donor of proton, and a neighboring proton receiver, that is the nascent proton, I mean the proton which is going to be transferred will have to be received by another atom, which is the proton receiver or proton acceptor. So, ESIPT has gained considerable attentions from both theoretical and experimental scenarios due to its extensive application in chemical and in biochemical fields. So, it is a very important thing, and it is very elementary, and I mean it is very fundamental in nature. So, excited state reaction, think of a molecule like 3-hydroxyflavone, which is a classic example, that you have got this you see that this is a molecule where this proton is initially attached to this end of the molecule. Okay. So, this is a schematic of the molecule. Okay. Now, it is basically the deactivation by the excited state intramolecular proton transfer. So, you have got the excited state of the molecule, and then this molecule gets deactivated by various means. It can undergo deactivation by a radiationless transition, okay, radiationless transition, and that leads to coming back to the ground state of the molecule. Or what will happen, that this there are other things may happen, like electron transfer, that may be possible, maybe energy transfer, or in this case what we are focusing is the proton transfer. You see that proton is getting transferred, I mean schematically it is shown like here that as I have shown over here, like this is your molecule, the schematic of the molecule. Okay, initially proton is here, and then what is happening, that you have got a molecule, I mean another system where this proton is shifted from here to here. So, proton is now attached over here. Okay. So, it is one, initially it was at one position, now it is transferred to a position x. So, it is a 1x type of transfer. Okay. And as a result of which, so this side becomes delta minus and this side becomes delta plus, okay, or maybe it may be minus and plus, because this H plus is transferred from here to here. So, this region will have excess of minus charge density, and this region will have excess of plus charge density. So, classic example is 3-hydroxyflavone. So, this molecule is widely used for this type of exploration of the excited state reaction. So, this proton is the proton, this proton is the proton which is getting transferred from here to another position. Okay, this is the schematic of this process, that you have this, this is a Jablonski diagram involving this proton transfer. So, you have got this S0, this is your S1, and these are various vibrational levels. Okay. So, you excite the molecule with some radiation H nu. Okay. So, molecule gets excited from here to here and then what will happen, that a proton transfer will take place leading to another state. This is your proton transfer state S1 prime, and then this is your another state S0 primed, okay, and then this is your proton transferred state, this is your starting molecule, and this is a proton transfer PT state. Okay. So, this gives rise to emission. in a shifted wavelength. So, h nu f primed, it may be there may be non-radiative de-excitation as well. Here this is also possible, non-radiative de-excitation, okay, and intramolecular vibrational relaxation. So, this process is your proton transfer process. Okay, this represents your proton transfer process. Proton transfer. Okay. So, proton transfer gives rise to, say, if it is OH type of molecules, you have like something like, say, okay. So, this is your all form, enol type of form, and then when proton is getting transferred, so this part becomes keto. Okay. So, maybe proton transfer thing, maybe it may be the keto form. Okay. And this corresponds to reverse proton transfer or the back proton transfer, giving rise to, so, reverse or back proton transfer, back proton transfer, giving rise to original molecule back. Okay. So, you see that this proton transfer is taking place in the excited state, giving rise to a proton transfer state. So, if you look into the emission profile of the molecule, you will be finding that you have got, say, if you get an emission which is called your locally excited emission, LE, and this is your proton transfer emission, then in this side lambda is increasing and this is your intensity, fluorescence intensity, then maybe you can expect to have, this is your normal emission and maybe a shifted emission. Okay. So, this is your normal emission, normal form, and this is your proton transferred form. Okay. So, you can expect a shifted frequency in the red side of the emission spectra, because this gap is less. Okay. So, typical example like benzazole type of derivative, you see that this is your enol form. Okay. It starts from enol, the ground state is enol. So, this enol system, if I write down this benzazole type of system, you see that you have got this system, then N, then double bond, then X, okay, and then this is your and this is your OH. Okay. So, this is your enol form, in all. Okay. So, and you can have this, say, if this is X can be, this X can be NH, O or S, this X can be NH, can be O or can be S. So, this is your enol, then you will have enol in the excited state, okay, and then there will be excited state intramolecular proton transfer, so that your proton transfer state will be when the proton is transferred, your molecule will look to be like this X, this N, H, and then this double bond, and then okay. So, this keto form is there, okay, and this is your keto star. Then this keto will fluoresce to give you keto in the lower energy, or the keto in the ground state. So, you will have keto, then this keto will come back to your enol by reverse proton transfer, that is, this proton in the ground state, this proton is transferred from here to here, giving rise to your this original enol back. So, it is basically, you see that this is your you have got this two minima over here, and these are coupled to each other, and you see that this minima corresponds to, this minima corresponds to your this enol, and this minima corresponds to enol star, it is in the S1 state, and this corresponds to your keto form in the excited state, this corresponds to the keto form in the ground state. So, you see this is your absorption process and this is your emission process. So, absorption gap is more than the emission gap. So, you will be having redshifted emission. So, now if you look into the decay of the excited, suppose if this is fluorescing, then you will be finding that there you can expect some decay, because excited state is getting deactivated. But whenever you monitor this emission as a function of time, that is when you monitor this time resolved profile of this particular system, in this region you will be finding that there is a rise of there is a rise which substantiates that this excited state proton transferred species is forming. So, so depending on the slowness or the fastness of the process, since it is an intramolecular process, generally this transfer process is fast. So, depending on the time scale of observation, you can, I mean, if you can go to the much faster time scale, if the process is very fast, then maybe you can see the rise or the growth of this excited ensemble of keto. But if your detection system does not have that capability to detect this faster event, then maybe you won't be able to see it. So, depending on the resolution of the system, resolution of your detection system, you may observe this growth of this keto star form. So, you see that this is hydroxyphenyl benzothiazole. So, you see that this is your enol form and this is your keto form, and you see that this is your enol absorption spectra, enol absorption spectra, and this corresponds to the keto emission spectra, and there is a huge shift here, there is a huge shift. So, enol absorption is taking place around say 350 nanometer, and your keto emission is taking place around 550, that is the maxima. If you think of the maxima, around 550. So, you see that there is a huge Stokes shifted emission when there is a there is a proton transfer in the excited state. So, this process is proton transfer in the excited state. So, you see that there are factors. I mean, if you have a solvent which promotes this form, or maybe the solvent, if the solvent is promoting this form, then there is a problem. Otherwise, I mean, problem in the sense that maybe you in some cases you may not actually see this proton transferred emission, or maybe, or if this form is promoted by your solvent, then it may be difficult to observe this one. But in normal case, you can observe this one as well as this one in the excited state, depending on the type of molecule you are considering. So, here the example is taken from this particular reference, that this corresponds to the keto emission. You see that there is huge Stokes shift, about 8,000 centimeter inverse. You see there is a huge shift. So, it is centered in the UV region, and this is centered in the visible region. And of course, this is not in the ground state, but it is in the excited state. So, within the within the lifetime of this excited state, excited enol, this this proton is transferred to here, I mean from here to here, and thereby this form is generated, and as a result of which maybe you can see this emission. This is a typical emission spectra, that is in the red side. So you may observe also this locally excited emission as well, but the most important thing is that the proof is that you are observing a large red shifted emission due to ketoform. Okay. So that's why we always talk about acid base reaction or something in the ground state, but interestingly this is basically related to the acid base property of this donor and acceptor, where the donor and acceptor, these two are located within the same molecule. So if this nitrogen has a strong preference for accepting this hydrogen, then this will take place. And you see that in both the cases there is a 6-membered cyclic state, okay, like this one. If you think of this particular molecule, say N, then I am just drawing this part. Then this O and then this H. So initially what is happening, that there is a hydrogen bonding interaction, and then this proton is transferred. So this bond weakens, so becomes weak, and this bond becomes stronger, and as a result of which this hydrogen is transferred from. So the separation between this oxygen hydrogen increases as the proton is transferred from this oxygen to this nitrogen. Okay. So this is a typical ESIPT reaction scheme, that this is your S0, this you pump to S1 state, and this is your wedge form, that is enol form, and then this enol form, this nitrogen and hydrogen coming close to each other, so that there is a hydrogen bond formation taking place. And then in some time what is happening, that in some time this hydrogen is getting transferred from here to here, and this double bond is rearranged so that this ketoform is generated. So and there is electronic configuration change. You see that here in between these two, the hydrogen is neither strongly bonded to oxygen or it is strongly bonded to nitrogen. So it is in the midpoint, and then with time what is happening, that this bond shrinks, so that this hydrogen is coming within the bonding distance of nitrogen, and this bond ruptures. So you see that this is a proton transfer. After the proton transfer has taken place, this is happening. Now you can expect that this system will emit. So this emission is from the ketoform, and this corresponds to, this corresponds to reaction, but several modes will contribute. Modes means various motions within the molecule are responsible for this hydrogen to get transferred from oxygen to nitrogen. Okay. So this is your S1 potential energy surface, and this is your S0 potential energy surface. So gap is reduced over here, that is why the emission is in the red side of the spectrum. Okay. So this is a typical example. So this is another schematic, that you have enol form. Generally most of the examples are related to the keto enol enol form. So it is basically tautomerism in the excited state, electronically excited state, keto enol tautomerism. So you see that it is your enol form, this is your keto form. So this tautomerization is taking place in the excited state. You see that S0 to S1 excitation by light, and then excited state intramolecular proton transfer, then internal conversion. It may be internal conversion, or may be emission, or it may be emission. So so emission will give rise to a red shifted emission, red shifted photon, and then back proton transfer giving rise to enol form back. So this is a typical simplified schematic which talks about this which talks about this configuration change, that hydrogen is transferred from oxygen to nitrogen. And since hydrogen is very small in size, so I mean basically and also it can form hydrogen bonds simultaneously with this nitrogen and oxygen. So, it has got the probability of being attached not only to the oxygen, but also to nitrogen, and then depending on the electron distribution on the nitrogen and also the electron distribution on the oxygen, it may strongly bind with oxygen or it may strongly bind with nitrogen. Ultimately, it leads to either the enol form or the keto form. Okay, so that is why this excited state intramolecular proton transfer is a fundamental phenomena, is a very important phenomena that is generally observed when a molecule is getting excited and has got the option to have this enol form and the keto form. That is, it has got the option to have a cyclic maybe 6-membered hydrogen bonded hydrogen bonded state, so that after this hydrogen bonded state is formed, then this hydrogen is getting transferred from the oxygen to the other heteroatom. Okay. So, this is about this excited state intramolecular proton transfer. So, this excited state intramolecular proton transfer, other than that there may be excited state intermolecular proton transfer, that suppose you have got one molecule which is in the excited state, but it is not able to form this say intramolecular hydrogen bonded say transition state, say like this. Then what is happening, that maybe it will try to form like this. Suppose you have got this is say hydrogen end and say this is your nitrogen end. So, it will form maybe this type of this intermolecular hydrogen bonding, or maybe hydrogen bonding will take place with the solvent molecule. So, that solvent will be the receiver of proton, or maybe it is the supplier of proton. So, that is another possibility, that is called the excited state intermolecular proton transfer. Now, we will switch on to another important topic which is intramolecular charge transfer. We have just finished discussion of this excited state hydrogen or the proton transfer. So, it is happening within the molecule. Okay. So, here this proton is switched from one atom to another atom, okay, and that is called the that happens in that occurs in the excited state. So, that is called the excited state intramolecular proton transfer. So, talking in line with this fact or in line with this phenomena, we can also we can also have another type of process, which is called the charge transfer. So, we have talked about this charge transfer, say like exciplex formation. So, what is exciplex? As I told you that in some other class, that it is the excited state charge transfer, okay, excited state charge transfer followed by it is a charge transfer complex formation. So, that is electron is transferred from one donor to another acceptor, so that you can get like plus and minus, and then this plus minus will form a complex, giving rise to some some emission, and that happens in the excited state. That's why it is called the exciplex formation. So, it is basically a case of intermolecular electron transfer. Intermolecular electron transfer means transfer of electron from one molecule to another, where either the donor or the acceptor is in the electronically excited state. Okay. Now, in case of intramolecular charge transfer, what is happening that if we can have a system, such that this donor and acceptor are bonded to each other, okay, in such a way that the charge which will be given by the donor can be accepted by another part of the same molecule having the property or the having the property to accept that electron, accept that charge. So, in this regard there are plenty of examples available in literature, of which one classic example is your trans 4-dimethylamino 4-primed nitrostilbene. You see that in this particular molecule you have this dimethyl amino. Think about of this particular part, I mean up to this benzene ring. You see it is dimethyl aniline. Okay, dimethyl aniline. We talked about this pyrene dimethyl aniline exciplex system, where dimethyl aniline in the ground state transfer an electron to the excited pyrene to pyrene star, then charge transfer is taking place from DMA to pyrene star, giving rise to pyrene DMA exciplex, that is pyrene minus and DMA plus, okay, DMA plus dot and pyrene minus dot. So, in this case you see that this is a potential donor of electron, and you see that this nitro group is a very strong acceptor of charge. I mean it has got a strong capability to pull electron towards this particular functional group. So, it is electron withdrawing capability. So, what is happening that when nitrogen gives one electron, then through this mechanism, I mean this push pull type of mechanism, what is happening that this electron is ultimately through this conjugation reaches this nitro. Okay, this reaches this nitro group, and as a result of which what is happening that in the same molecule you can have one part delta plus, another plus part delta minus. So, this becomes becomes dipolar in nature. So, what is happening that you excite, you are getting locally excited, then you can get a fluorescence from this locally excited and then excited state and then it may undergo some process giving rise to another intermediate state, and ultimately non-radiative de-excitation giving rise to the original state back. So, you see that charge is transferred from here to here. So, this can be a classic example of intramolecular charge transfer. There are plenty of examples. You see that you can have 4-dimethylamino-benzonitrile, which is given the short form DMABN, okay, dimethylamino-benzonitrile. So, you see that this is the molecule of interest. So, C triple bond N and then N methyl. Okay. So, this lone pair and then ultimately it goes to here. So, that this part, this whole part, I am not drawing this, I am just drawing in this way, that this part becomes delta plus, this part becomes delta minus, or maybe this part becomes plus and this part becomes minus. So, after the electron, I mean electron is transferred from here to this acceptor. So, the whole I mean this molecule becomes this dipole of the molecule, induced dipole, the dipole which is induced as a result of this electron transfer is becomes very high. So, you see that charge is separated, this side minus, this side plus, and it is through the length of the molecule. Okay. So, you see that a very interesting observation is there that in hexane you can get this simple band which is having, I mean emission spectra is like around 330 nanometer, 330 to 340 nanometer, you can have a strong emission band. And the moment you change the polarity of the system, or this moment you change the solvent from hexane to tetrahydrofuran, what you observe that now you can observe two bands. One is close to this one, this original, and another red shifted emission spectra. So, this is your locally excited, if you think of the locally excited state, this corresponds to the locally excited state. Okay? So, this band corresponds to the locally excited state, and even this locally excited state is there even in low polarity solvent like hexane. Okay? Now, after this charge has been transferred from this donor to the acceptor, there is a possibility that this Cn, you see that Cn single bond, there can be a possibility of rotation about this carbon nitrogen single bond, and as a result of which you see now this conjugation is lost. You see initially this is an extended this is having the extended conjugation. Now this conjugation is lost as a result of the fact that now these two planes are perpendicular to each other. You see that these two planes are perpendicular to each other. Okay. Initially it was like this, so that this particular part and this particular part can be connected by a strong conjugation, but the moment it is done like that, then this conjugation is stopped. So, this is called the twisted charge transfer state, and this twisted charge transfer state is as a result of intramolecular charge transfer. Okay. And this TIC state, this is twisted full charge transfer, and this is your planar partial charge transfer. Partial means a little fraction of this of this charge on this nitrogen is transferred from here to here, so that primarily this carbon nitrogen bond is single is still maintaining the single bond character. But the moment this there is a full transfer, maybe these two are now perpendicular to each other, so that these two rings, these two parts are now, they are not connected. I mean, electronically they are isolated to each other. Okay, and so this state is different than this state, and this particular emission comes from this charge transfer, twisted charge transfer state. You see that this part is delta plus, this part is delta minus. So, it is a case of partial charge transfer, and when it is twisted intramolecular charge transfer, you have got in the ground state d plus, d delta plus, a delta minus. After you shine with radiation, okay, it is still like d delta plus, a delta minus, and then this this rotation about this single bond, so that electronically now they are disconnected. I mean, this conjugation is lost. So, this part and that part, they are perpendicular to each other, and these particular species, I mean, this will be A minus. So, this particular species will now emit at a different region of spectrum, like you have seen here that in tetrahydrofuran, you can see a red shifted emission around 450 or 440 nanometer. There is an enormous shift. You see that from 330 to about 440, or 350 to 450, about 100 nanometer shift in the spectra, and this corresponds to the locally excited state, that is as a result of this excitation of this DMABN, ground state DMABN to the excited state DMABN, and there is no geometrical rearrangement like twisting of the system about certain, I mean about a given single bond. So, this is a schematic of this twisted intramolecular charge transfer, that is initially it was planar, after excitation still remains planarity, and after that its planarity is lost. So that now it is fully charge separated species. And maybe what is happening, that in less polar solvent this state will be promoted. Why this state will be promoted? Because this does not have large dipole moment. So, large dipole, since it is not large dipole moment, and suppose if you have a large dipolar system, then to stabilize the system you need to have a polar solvent or the solvent which has got higher polarity compared to a less polar solvent. So, higher polar solvent or higher polarity solvent will promote this particular charge, fully charged separated species than this species. So, that is why when you switch from hexane, that is a very low polar solvent, polarity solvent, to another solvent which is a tetrahydrofuran whose polarity is more, automatically this particular state is stabilized. Okay, this is a schematic representative taken from this paper and this website. So you see that it has got this locally excited state and another which is referred to as LV state, and corresponding emission is called the normal fluorescence, and LA is your charge transfer state, and this charge transfer state gives rise to anomalous fluorescence. You see that if you look into this particular geometry, you see that all are parallel. I mean, parallel means this particular this NME2, this NCC, then this C, and also CN, all are on the same plane. Okay. So, it is your locally excited species with maybe a little bit of charge being transferred from here to here, but in this case this NME, this NCC, this particular one, and this CCC, this particular plane, these are perpendicular to each other. Okay, so this corresponds to complete charge transfer state. Basically, charge is transferred to here, and then this particular this NME2 is twisted like this, so that this back transfer of electron from this cyanide system, suppose this is your cyanide. So, back transfer from this cyanide to this NME2 is not possible. So that, and also since in this case the charge is completely transferred from this NME2 to this CN. So, what is happening, that it is a polar system, I mean a species is polar, and it requires, I mean for its stabilization you require higher polarity solvent. So, in higher polarity solvent what is happening, that you can see this anomalous fluorescence as compared to the normal fluorescence which you can observe in the in the low polarity solvent like say hexane. Okay. So, geometry of the intramolecular charge transfer state, it is twisted intramolecular charge transfer. This amino group has perpendicular conformation to benzonitrile plane. You see that this one is like this, or maybe pseudo Ian-Taylor model with quinoidal quinonoid type. Okay, conformation like this particular thing, that here it is minus and then it is like quinone kind of thing. Okay. So, quinone kind of thing, and it is your pseudo Ian-Taylor type planar ICT, intramolecular charge transfer. You see that this minus is located far from this one. Okay, and it is a 0 degree species. It may be PICT or it may be it may be TICT. But so this may be the two possible cases. So that in this case also your charge, I mean charge separation is huge, and here back electron transfer is not possible as long as this geometry is maintained. okay, as long as this is maintained. Now, two-state conversion mechanism is this. This is your LE state, this is your ground state, as I already told that this is your excited, I mean this is ICT state. So, you know this I mean Ka, and this is your back transfer, this is a forward transfer. So, forward process is K, backward process is Kd. Now, ICT is generated. So, ICT with a rate constant K ICT, you know this fluorescence is giving. So, this is a red fluorescence and this is a green fluorescence, and of course, this is a high energy emission, this is a low energy emission, and this is your ICT state, and this is your ground state potential energy surface. So, this is a two-state conversion mechanism. So, this is LE state and this is your ICT state. Okay. So, Gabrowski et al. It is taken from this chemical physics letters in 1973, and also here in both in I mean same example, I mean it is here. So, in 1973 proposed an explanation, the anomalous emission which occurs I mean from a charge transfer state that is populated by a non-radiative transition from the locally excited state. Okay. So, this is your locally excited state. So, when you excite, this locally excited state is populated, and then from this locally excited state, this is transferred. I mean, in this locally excited state, what is happening? There is a from this locally excited state, this city state is gradually populated. Okay, city state is gradually populated, and the intramolecular charge transfer is accompanied by a rotation around this phenyl ring, and in nitrogen bond and twisted intramolecular charge transfer is achieved. I mean, you have this initially you have your locally excited this state in Me, and here it is C triple bond N. So, what is happening? That this initially when you shine with radiation H nu, then this LE locally excited state is generated, and this locally from this locally excited state this charge transfer state is populated by means of what? By means of your non-radiative by means of a non-radiative transfer. Okay. Basically which is shown over here, this process is non-radiative. Okay, it does not require any does not require any involvement of photon. Okay. So, it is transferred non-radiative transfer of electron from locally from this state to this state. So, as a result what is happening that this non-radiative transition from the locally excited state to this charge transfer state, so that this charge transfer state is generated. You see that it is excited over here, and then there is a crossing point. So, through this crossing point this state is populated. So, since this state is populated, so anomalous fluorescence is observed. Now, the point is when you use more polar solvent, so this CT state is more stabilized. So, it is if it is more stabilized, then probability of formation of this CT state from here is more. So, that is why in more polar solvent you can expect to have more intensity of the anomalous fluorescence as compared to the normal fluorescence. So, this is your normal fluorescence, this is your anomalous fluorescence, and Gabrowski et al. Proposed this explanation that is a non-radiative transition that leads to this LE to charge transfer state and giving rise to two-state intramolecular charge transfer. So, that is why this is a very this is another this is another interesting and important phenomena which is observed in case of this this organic molecules where the donor and acceptor, these two are coupled to each other by chemical linkages, maybe via this conjugation, okay, so that this transfer of electron is taking place from here to here in the excited state, and thereby interesting observations are there. Okay. So, basically here it is the case of intramolecular electron transfer, and if there is a possibility of twisting around some single bond, then maybe this because of this twisting, and this twisting is a non-radiative process, because of this twisting this charge is now retained by this cyanide system, cyanide moiety. I mean probability that this cyanide will retain this charge will be more, so that this back transfer will be less. Okay. And now after some time, what is happening, that maybe because of this thermal agitation, maybe it will come back, and at that moment what will happen, this back electron transfer will take place, or maybe some way by some other means this is this excited charge transfer state collides with some other moiety, or maybe it undergoes radiative, or maybe some some non-radiative de-excitation to go back to this dimethylamino benzonitrile in the ground state. So, this completes our discussion on this charge transfer, that is intramolecular charge transfer process, and excited state intramolecular proton transfer. So, in our next lecture we will take up some more similar events, and also this a bit of spin chemistry, that is effect of external magnetic field on this electron transfer or back electron transfer process. That is a very interesting event. So, we are going to take up in the next lecture. So, till then have good time. Thank you.